Hello students, welcome to Saraswati classes. Today we will be discussing octahedral complexes and the optical and geometrical isomerism in them. So initially I would like to say the octahedral complexes have 8 faces. Okay, when I say 8 faces I mean 8 triangular faces. So if you are taking a very simple complex such as Ma6 where the charge N can be neutral or positive or negative, M out here is the central metal ion and A is the monodentate ligand, which can be positive or negative or neutral. So this ligand can be positive, negative or neutral. Now if we were to draw the octahedral complex considering the metal and the donor atoms as spheres, then initially we begin by drawing the A and placing them along the vertices of a square, and then follow it up by placing the two other A or donor atoms along the z-axis, both top and below. And now if you think that we are joining these donor atoms, then we can see once we join 3 such donor atoms, then it makes a triangular face. So that is face 1, this will be face 2, that if we join it is face 3, and then if we join another one, then it is face 4. Since this is a centrosymmetric molecule, that has a center of symmetry, it will have 4 faces on the top and 4 faces below, and that would make up 8 faces for the molecule. Besides that, the molecule has 3 sigma planes of symmetry dividing it into equal halves, and one such sigma plane of symmetry can be easily shown by joining these 4 atoms over here. So this is the plane of symmetry that will be dividing the molecule into 2 equal halves. Okay, there will be a top half and there will be a below half. Okay, so there are 2 such more, okay, that are lying on the xz plane and zy plane. The one that we have highlighted over here is the xy plane. Now if we take another molecule, such as, we are discussing types out here, so if we talk about Ma5b, keeping other things same, so here we will say M is the central metal ion, A is not equal to B, and both are monodentate ligands, can be neutral or can be negative. Now out here, if we were to think the placement of these donor atoms, so let's consider the red ones as A. Okay, and let's think in terms of arrangement. What are the possible arrangements we can have? And the B atom I am thinking as another sphere which we are indicating by using a green sphere, and the metal is obviously in the black. Now can there be any other possible arrangements? No, because if you exchange any of these positions, say whether you exchange with the left hand sphere or left hand donor atom, or here the structure, new structure generated will be identical to the one that is already there. So out here what we will say that there is only one type of geometrical isomer possible here. Okay, and since the molecule again has a plane of symmetry, so no optical isomerism. Okay, where should be the plane of symmetry? The plane of symmetry should pass right through the middle of the green sphere, dividing it into two equal halves along the z direction. Okay, so there can be no optical isomerism. Optical isomerism will only be shown in octahedral complexes when there is no plane of symmetry. Okay, next let's take examples of MA6 and MA5B. So for MA6 we will say examples can be obviously homoleptic complexes, so it will be say FeCN6 3 minus, or it can be FeH2O whole 6 3 plus, can be MoCO6 etc. What about MA5B type of complexes? Then very standard examples can be CONH3 whole 5 Br 2 plus, or it may be FeH2O whole 5 NO, that is the brown ring complex, or it can be nitropres or nitroprusside complex. All right, let's have a look at another complex or another type, which we will be calling as MA4B2N. Question is, can there be a geometrical isomerism in this complex? Because in the above two cases there was no geometrical isomerism. We will say yes. Again, out here M is the metal ion, A and B are monodentate and they are not equal to each other. So what are the geometrical arrangements that are possible? So we will say if we place all the A atoms along the square plane, and if we place the B atoms in the Z direction top and below, then we can think that this particular arrangement, now that we see where the B atoms are at a angle of 180 to each other, that is a B angle is 180, so this particular will be called as a trans isomer, whereas in another arrangement when the B atoms are having an angle of 90 to each other, that is this one, this is the trans. So we can say that this will be another set of arrangement that is possible for this type of complex. So this arrangement where the two B atoms are 90 degree to each other, or the angle between them is 90 to each other, will be called a cis arrangement. Okay. Again, interestingly, if we were to consider the dipole moments of these two complexes, that is the trans one and the cis one, we will say for this one it will be 0, and for that one it will not be equal to 0. Okay. So obviously for MA4B2 complex we will have GI. So it shows GI. There is no doubt about it. Can it show optical isomerism? We will say no, because if you think of a plane lying in this direction, then it is dividing the trans molecule into two equal halves, so no optical isomerism can be possible. Again, similarly, if you think a plane passing right through this direction, okay, the molecule will be divided into two equal halves. The molecule will be divided into two equal halves, and hence again we will say that no optical isomerism is possible for the cis isomer also. But what is important is that there is a difference in polarity between the two such geometrical isomers. Next, let us consider another complex which we will say as MA3B3. Again, same notation as we have used before. Again, A is not equal to B, and A is the central metal atom. So what kind of geometrical arrangements are possible for these two? Let's have a look. Now, if we place A in such a manner that all the A donor atoms are having an angle of 90 degrees to each other, and similarly all the B atoms are having an angle of 90 degrees to each other, then such arrangement, if we were to connect the donor atoms, then what we can see clearly is that these A atoms form one face, just like that. They are lying in one face. Similarly, the B atoms are also lying in one face. So such an arrangement, when the three donor atoms are lying in one face, will be called as facial, also known as the FAC isomer. However, if we want to move into a different arrangement for the same isomer, for the same molecular formula, if you want to move into a different isomer, then what we will say? I suggest that you place two such A atoms at an angle of 180 to each other. This is the easiest way of finding the other isomer. Similarly, what will happen that you have to place the other two B atoms also at an angle of 180 to each other, okay, and the other one obviously at an angle of 90. Now this type of arrangement, when we have the A, two such A's at 180 and one such A as 90, and two such B's at 180 and one B at 90, this type of an arrangement where no three atoms are occupying the same face is called the Meridionial Isomer, or known as MER. So from a facial isomer, if you want to move into a Meridionial Isomer, just remember that you have to place the two similar atoms at an angle of 180 to each other. So now if you connect the donor atoms, what you can think of is it is forming a triangle like this. Okay, but they are not lying in one face. Next, let us consider another complex in which we have Ma3B2C. Again the similar notation. M again is the metal ion. A is not equal to B, which is not equal to C. Now let us see what other arrangements we are possible. So obviously, since there is a A3 unit, so obviously there will be a facial isomer and the other ones will be meridional, as we can say. So obviously if we place the A such that the angles between them are 90 to each other, then the other arrangements what we can make is B are lying at B and C are lying at like this. So this unit wherein we can see already that if we join the A atoms, they are lying in one phase. So this particular unit we will be calling it as FAC or facial isomer. However, one may ask, sir, can we place C out here and B over there? Even if you do it, the angles between the B and C will not change. They will always remain as 90 because as you can see here the two B's are at 90 degree to each other and B and C are also 90 degree to each other. Okay. There can be no other angle achieved by interchanging the positions. So there will be only one facial isomer. What about if we keep the two A atoms at 180 to each other? So we are now placing the A atoms at 180 to each other. Let's see. So obviously one of them will be occupying 90 degree to both the atoms. Whether you consider this one or you consider that one. Now you think of placing the B. Here both the B's are at 90 degree to each other, but the C is having an angle of 180 with one of the B's atoms and 90 degree to the other B donor atom. Can there be another possibility? Oh yes, as you can see, I can now have both the B atoms at 180 degree to each other. When I am placing both the B atoms now at 180 degree to each other. So I will place one of the C's out here like this and keep the positions of the A donor atoms same as before. So now what we see is that there are two possibilities or two types of Mer isomers in respect to the FAC isomer. In one of the Mer isomers, I repeat, the angle between the B and C is 180 and 90 respectively with the B atoms. And in another Mer isomer, we are seeing that the two B's are lying at 180 to each other, but with the C, it is 90 to both. So basically, we will say now for the complex Ma3B2, there are three geometrical isomers. Okay, and mind you, this question has come many times in many competitive exams. Let's consider another one such as Ma3BCD, where A, B, C, D are all the donor atoms, different donor atoms. So A is not equal to B, not equal to C, which is not equal to D. And M is the central metal ion. Again, since there is A3 unit, so we will say there should be one facial isomer over here. And as I have taught you how to write the facial isomer, just keep the angles 90 to each other and then you can have the B, C and D. Since the angle between DC or BC or BD all are 90, so interchanging any of the positions, okay, there will be no new angle generated between these set of donor atoms. Okay, so there will be no such new facial isomer possible. Let's think of the Meridionial isomers. So for that, the trick I have shown you is that you place both the A atoms at 180 to each other, and the other one, obviously, you place in any of the positions, but it will always be 90 with respect to both the A's. Now, if I keep the position of B fixed out here, then I can have a C out here and then a D. Let's think another arrangement wherein I will place in place of D C. So I have already placed C. I have kept B position fixed. So D will be obviously occupying this one because the other positions are taken up by the A atoms. We will not be changing these, otherwise it will lead to confusion unnecessarily. Now, in one of the arrangements, we had B and D trans or 180 to each other, B and C 180 to each other. What is left? D and C are to be 180 to each other. So you will be thinking of another arrangement in which we will be placing the D atom or D donor point trans to C, and the rest of the positions are obviously taken by A and B. So now what we see, that there is one FAC isomer, but there are three MER isomers possible. In total, we will be saying there is out here 4 geometrical isomers in total possible. However, if we have been given Ma2, B2, C2, one should remember that there is, or one can check, there is a possibility of 5 geometrical isomers out here, out of which one of the GIs has no plane of symmetry, which means it is optically active. What I would do is I will help you out with the optically active GI. The rest of it one can find, and I will tell you the trick to find the optically active GI. Suppose you have the M. All you got to remember is that you got to place A at 92A, B at 92B, and say suppose C, the donor atom C at 92C. Once we do it, what we will realize is this particular molecular arrangement has no sigma plane of symmetry possible for it. This will not be having any sigma plane of symmetry possible for it. That means there will be another unit which will be a mirror image of, say, this molecule Roman 1. So what will be that mirror image? How to draw the mirror image? Place a mirror plane and place the atoms at an equal distance. Okay. So suppose we have for the A, sorry, not A, this one, this will be C. So there will be a C, another C. Okay. Then we will be placing the B's, the B donor points, and finally we will have the A donor points. So what is the relation between 1 and 2? We will say they are enantiomers to each other. They are enantiomers to each other. Similarly, again a factual question that one can remember, instead of drawing all the isomers, which would be a wastage of time, M, A, B, C, D, E, F. So these are the donor atoms that have been given to us, and all of them are unequal to each other. That is, A is not equal to B, which is not equal to C, not equal to D, not equal to E, not equal to F. There will be 15 geometrical isomers possible, and all lack the center of symmetry. Sorry, not center of symmetry, plane of symmetry. Plane of symmetry, or the center of symmetry. Plane of symmetry. And so we will say each one is optically active. Each one is optically active. That means there are 30 optical isomers, or 15 pair of optical isomers. Okay, that is what can be said. Let's take another example in which we are now considering MAA B2 type complexes, where AA, if you have followed the last lecture, you will know this is a symmetrical bidented ligand. Alright, and B out here is a monodentate ligand. Now what are the possible arrangements? So for the bidentate ligand, as I have explained before, A and A are connected via a curved line, which is indicating that there is an existing chain over there. And mostly these type of bidentate ligands can take up the positions or a bite angle of 90. So if we consider that, then there can be an arrangement like this possible, and we will place the B donor atoms top and below. Now, just as in Ma4B2 complex, we will be saying whenever the angle between the B donor atoms is 180 degree, we will call this as a trans isomer. This angle out here is the 180. So this is obviously a trans isomer. And similarly, what other arrangements can we have? So what we will do, we will avoid this this particular arrangement by placing the B atoms in the 90 degree to each other, and rest of the positions we will take up by the A atoms. So if we do so, That is how one has to approach, and it will lead to the correct answer. So what one can connect these two atoms over here in the following manner, as I am showing. It can be like this, okay, and like that. Suppose this chain, I'm saying, is lying behind. So if I'm saying behind, I will indicate it by a orange line like this, okay. If I'm indicating it is lying behind, or let's say I'm indicating it behind, so I will draw this as a dashed line like this, okay. And if I'm saying it is lying on the front, this chain, then I will indicate it by using a thicker line, okay. Now this particular arrangement will be having no plane of symmetry, okay. This particular arrangement will be having no plane of symmetry, but trans is having a plane of symmetry. How it is having a plane of symmetry? If you just follow this over here, just have a look. You have a another A like that, and if we were to join this A via this yellow line and consider a plane that is lying connecting this A donor atoms, then obviously we can say that this particular sigma plane will be dividing the molecule into two halves. However, in case of this molecule, we cannot find any such plane. So it means this molecule, if it is having no such plane, it will be having a mirror image. And how do we draw the mirror image correctly? So mirror image means always lateral inversion. So the donor points will be lying at an equal distance from the mirror, okay. Like this, we will draw the B, maintaining an angle of 90 degree between each of them, and then we will be having the rest of the positions occupied by A out here. Now if this chain was front, in the initial case this chain was front and that was behind. Now in the next mirror image, something that was front will go behind and something that was behind will come front. So to keep that clarity, we will draw this particular chain in the front, and that particular chain we will draw behind. And that is how we indicate the two optical isomers that are possible. So if this is trans and when the B are having 90 degree between each other, this will be called as a cis. So out here for this molecule MAA2B2, we will say there are in total 3 stereoisomers possible, out of which there are 2 geometrical isomers, which is cis and trans, but the cis form can show optical activity. So it is the cis one that is showing optical activity because it is having no plane of symmetry. Alright. Now if you want to be a little more correct, then you draw the molecules and then think of a mirror plane that will be keeping both the molecules at an equal distance, or the donor atoms, okay, just to be a little more correct in your drawing. Okay, so what we know now, that if we call this to be as 1, this to be as 2, this to be as 3, then out here we will say 1, when we consider the relationship with 2, it is showing GI. 1 in relation with 3, we will show GI, but when we are calling 2 and 3, they are showing optical activity. Let's consider another one. Say now we have a molecule of the type MAB whole twice C2. So now we are considering a bidented ligand which is unsymmetrical. Unsymmetrical bidented ligand out here. And so let's say it like this, AB. And C out here is our monodentate ligand. Okay. So what are the possible arrangements? Keeping MAA2B2 in mind, what we will do is we will draw the trans one first. So we have AB, AB, and then we have the C atoms placed in this form. So this is one arrangement that is possible for the trans. What other arrangement can be possible? If we keep the A donor points at an angle of 180 to each other like this. Here it was 90 and here it is 180. So that is the difference. And C usually takes up the positions that it has to, which is again keeping them at 180 to each other. So now we can see for this type of a MABC2 type of a complex, there can be two such trans possible or two such trans arrangements possible. Interesting. If you just change from a symmetrical to unsymmetrical bidentate ligand, two trans are possible. What about the cis isomer? In the cis isomer, we have to remember that we have to keep the C donor atoms at an angle of 90, which we have kept. We have the A and then we have the B. Then we keep the B and then we keep the A. So this is one type of arrangement in which again we can say that this is lying behind and this is lying in the front, and that is why we are indicating with a thick line. Okay, but this is in the dashed line form. So what is the mirror image of this molecule? Obviously something like that. Forgot to circle out the donor atoms over here. So now we will play the B atoms. Okay, and then we have the A atoms. So this will be a thick line and that should be a dashed line, just to indicate that one is lying above and one is below. And that is our mirror plane. Okay, let me use another highlighter. That is our mirror plane. Okay. Now, is there another possible arrangement for this cis isomer? Yes. We have kept out here, if you notice, the A atoms or A donor points trans to each other, even in this one. What about if you keep the A donor atoms or the B donor atoms trans to each other? Let's think about that. So now here we will be keeping the B donor atoms trans to each other. So that is one arrangement. And the C goes or keeps an angle of 90 between each other. There is no doubt about that. Again, we join the lines. Suppose this one we have kept in front and this is behind. So that means in the mirror image, A is out here, then we have M, A is out here, then we have B, we have B, and then we have C, we have C, like that. This will come in the front because it is the mirror image, and this chain will come in the back, indicating these are two separate isomers and they are basically the mirror images of each other. So now this is cis, this is cis, okay, and 1 and over here 2 are basically enantiomers to each other. 3 and 4 are also enantiomers to each other, wherein this is also cis, okay. So basically out here we will say there are 6 stereoisomers possible. Okay, and that should be our answer. Now here for the complex MAA3, where AA is a symmetrical bidented ligand, I would like to say over here that for such complexes, GI is not possible, but OI is. And how the arrangement is? So over here, all the donor positions will be taken up by the A atoms. So you just draw the 6 arrows connecting to the metal, indicating the coordinate bonds, and we have a A, 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 and then if we were to join, then let's say this is the behind, so this chain, if it is lying behind, the one below is lying in the front. All right, so what will be possible for this particular isomer? We will say there is no sigma plane of symmetry for this molecule. There is no sigma plane of symmetry for this molecule, and hence what can be said is that its mirror image will be of this kind. So again you place the A atoms occupying the octahedral donor positions. Here it was behind, so obviously in the mirror image it will be in the front. So to indicate that, we will use a thick line, and this one will be in the dashed line, indicating that this particular chain is lying behind, and this is within the plane. So out here the mirror images are as follows. So for MA3, MAA whole thrice, we are only having 2 sets of isomers. Now what is important to understand over here is that when the A atoms, the connectivity goes in the clock hand direction like this. So this is the A atom, and the connectivity with the other A atom goes in the clockwise direction, just like that, then this will be called as a delta isomer. However, when the connectivity of the A atoms are going in the left hand side, like that, it will be called a lambda. Okay, so instead of using D and L notations as we use in organic chemistry, we are using delta and lambda notations for indicating optical isomerism in inorganic complexes. Again, let's take another example in which we will be using an unsymmetrical. So suppose we are taking over here MAB whole thrice N0 plus minus. So AB out here is what? It is a unsymmetrical bidented ligand. Now over here what we can think, it all depends on how the placement of the donor atoms happens out here. So again, for sure we will only be having over here optical isomerism possible. Okay, this will be showing optical isomerism. But how many optical isomers are possible? Let's see. Suppose we place A, B, A, B, A, B, and our arrangement is something like this. Okay. So obviously, as we have explained, for such a arrangement, there will only be optical isomerism possible. So what will be the optical isomer? Let's draw it. So out here we have M, this is a B, this is the A, again this is the B, this is the A, this is the B, this is the A. So like that, okay, like that and like that. So this again is N0 plus minus, this is N0 plus minus. So this will be what? Delta or lambda? We will say this is lambda and that will be delta. Okay. Now here is an interesting part. If you join this A atoms with a different line like this blue line, what you can find is that the A are lying on one particular face. Similarly, your B are lying on one particular face like this in both the structures. Okay. So this is one possible arrangement for the optical isomers. What is the other possible arrangement that one can think of? So how we will be doing it? What we will do is we will put the A and the B like this, but in this position we will have one A, alright, and this will be occupied by B, and we will keep the rest of the things as same as that. Now if you join, you will see that in this particular structure the A are not lying on one particular face. So that means this molecule, that is the structure 1, and if we call this structure 2, this we are saying structure 3, and this we are saying structure 4. So 1 and 3 are not equal. 1 and 3, they are not equal. They are different. Okay, so what we will say that for the structure 3, the mirror image will be what? Again, we have to imagine one mirror plane and place the donor atoms. So this is A, this is your B, you have another B out here, and then A out here, and there is another A. Okay, this is the B and this is the A. So if you can imagine one mirror plane dividing these two molecules 3 and 4, and now if we connect as before, we will say this is the connectivity like that and like that. So if this is our delta, then this will be my if this is our lambda, then this is our delta, because again we can see that this is going in the clockwise direction, whereas this is going in the anti-clockwise direction. All right. So what can we say when we are having a complex of the type MAB3 whole thrice? Then there are actually not 2 optical isomers, but there are 4 optical isomers possible. 4 in total optical isomers possible. Okay. Similarly, one can try MAAA whole twice, okay, which is obviously a AAA is a tridentate ligand. Okay, one can give it a try. And at last, to end this section, we will be considering a hexadentate ligand, which is basically a MEDTA complex. EDTA is your ethylene diamine tetraacetate. And what kind of arrangements are possible for this complex using the donor atoms? And what kind of isomerism it will show? We will say it only shows optical isomerism. Why does it show optical isomerism? Because it has no sigma plane of symmetry. So the EDTA complex, we know there are 2 nitrogens. So we will place these 2 nitrogens like this. And there are 4 acetate groups. So we'll place the O in one of them like that, in another one like this. And try to maintain the connectivity. So out here we have something like this. All right. Then we have another one. So basically, let's take this molecule a little down. Okay. So this is one O, and so this is the connectivity happening from the atoms like this. So we have something like that, and so this is one of the arrangements. And what can be the mirror image? Just the opposite of it. So what we will do, we'll place the metal over here, and then we will place the nitrogen atoms like that. Connect the nitrogen atoms over here. Oh, that is the connectivity, right? So it's better to, yeah. that is CH to CH2. Then we will place the O atoms top and below on the square plane and then try to connect them with the maintaining the acetate bridge. So here what will be happening? This will be something like that. So this is double bond O minus. Out here this will be the single bond O minus is connecting. So we'll just do the reverse on the top over here. So out here it will be the single bond O that will be connecting and the double bond O will be left. And out here it will be the double bond connecting and the single bond O will be left. So that is how we have to maintain this parity. And then we will draw the mirror plane. So we will say for a EDTA complex, there will be two such optical isomers, okay, and we will be calling them as enantiomers. Okay. Thanks for listening. Keep visiting Sarvasa classes for the rest of the next lectures and have a great day.